Students, welcome to the second part of the lecture 4, and here we are talking about or discussing about regression. And initially I talked about linear regression, linear models, and I explained you various kinds of things with different mathematical expression. You can go back to the my last lecture, lecture number 3 also, and lecture number 4 also. Okay. So let us start get into more of that. If you do not understand something, please get back to me or the TS, we can explain you further. So now we are going to talk about non-linear part of the regression. Okay, so that's something which is very important for you to learn. So as you know, non-linear, all of you know, right? Non-linear expressions are very common in material science, and they are expressed in terms of what? You know that, right? They are expressed in terms of polynomials. You know that? So let us talk about it. I erase this part. So we are going to discuss about first non-linear regression analysis. So what do you understand about non-linear? Basically they are polynomial equation. I write one of this, f(x) is equal to a0 or a0 plus a1 x plus a2 x square plus a3 x cube plus an x to the power n. This is a generalized nonlinear or polynomial equation which can fit any equation. This is in algebraic form. You can also have sinusoidal equation, logarithmic equations, exponential equation, right? You can also have that. So you can also have f(x) is equal to be a0 plus a1 sin x. You can also have log you can also have exponential equations. Correct. The best possible exponential equation is the diffusion coefficient dt is d0 exponential minus q by RT. Am I clear? You know this, right? So simply you can take log on both sides and make a linear relationship between dt log of dt versus 1 by t. This is possible, right? But this is originally an exponential relationship, right? So therefore all this comes under the nonlinear regression analysis. So how to handle this? Am I clear? That is what is the question we are discussing. How to handle this nonlinear part of the equation. I think I have given you some idea in the last lecture. Let me tell you that we can always write down these nonlinear equations in a very nice manner. Okay. What you can do? Very simple. We can write down in vectorial form nicely. Please follow me. It is very easy to remember. So 1 x, this is a matrix, 1 x1 x2 x3 to xn, 1 x1 square x2 square x3 square to xn square. Similarly 1, you must be thinking why I am using 1, it will be clear to you now. this is Q actually. Then you can directly go to n power. This is my x. Now I can write down W's Am I clear? So you can multiply. So that's why 1 is used, W0 plus W1 into x1, W2 plus W2 into x2 plus W3 into x3 and goes on. So the same, and this side y1, y2, y3. In generality, we can write down yi is equal to what? W naught or W0 plus sum it over j 1 to n Wj xj to the power j. Am I clear? So you can clearly see W0 plus W1 x1 power 1 for J1, W2 x2 square, W3 xc square, x3 cube and goes on. That is the generalized relationship for such a kind of data. Very easy to remember in the matrix form, very easy. If the moment to write in this form, it is very easy to remember that. So now you can use residual sum of square, RSS W, this is nothing but summation of y0 yi minus W0 plus j going to 1 to n Wj xj to the power j this is I, that is the residual sum of square. Am I clear? Very easy. We take the differentiation between these two terms. So, one can always do the difference, the minimization of RW, the RSS, that is this I just done in the last class, last part of the lecture, W0 put a big 0 there. So, that means each of these expressions has 0, first derivatives, first order derivatives are 0. So, then you can easily calculate or easily find out the values of this coefficient W0, W1, W2, W3, W4 easily. Remember that this analysis which I shown you just now does not consider error involved that, right. You can have error involved in each of these measurements. To give an idea, let us say you are measuring temperature of a material when you are heating up. How do you measure? Using a thermocouple. This thermocouple is sensing the temperature from the sample. No thermocouple in this world is perfect in measurement of temperature. There will be always some error involved, and this error must be accounted when you want to take in your data. That is why many of these data will have x plus minus something, right. You can see the different data sets. So, that plus minus is your measurement error. How do you take care of that? That can be easily taken care of, no issues in regression analysis. You can add another term called error, right. So, this is nothing but another term. So, if I want to write the equation now, this will be equal to this, right. That is value of yi, correct. So, now we can do the same analysis, same residual sum of square and the similar analysis. I leave it to you for your purpose. So, I hope you understood the meaning of linear and nonlinear. So, we are not going to talk much other things like log or exponential, sinusoidal. This also can be represented in terms of the this kind of functions. All if we know that exponential function, let me write down here, exponential e to the power x is what? Is 1 plus x to the power 1 factorial x square factorial 2 like that. So, that is nothing but infinity series in terms of the x, right, as a polynomial. Similarly, log can be also represented in the same way. So, therefore, all this function can be also written in this way and we can do that. You may not write it also because this is a very easy to differentiate. So, you have to find out the minimization of the residual sum of square, you need to differentiate this function, it is very easy to differentiate. So, you may not need to write in terms of x also, but if you want you can do that. You can always write in terms of x and make this equation possible and find out that. So, that is about the polynomial expressions. Now, I just want to tell you this nonlinear polynomial or linear equations are very good, nice, but they have one critical problem. You know, there are two critical problems of this. So, let us talk about that critical problems which you can face and how can you solve that. Okay. The next 10 minutes or so we will do that. So, I will just tell you the problem first, just a minute. I will give you example of that, what are the problems we can face. So, linear regression analysis or even nonlinear regression analysis, both of them actually, they are very essential whenever you are doing some analysis in data informatics, but many advanced ML algorithms are developed which are basis on these analysis, nonlinear, linear regression analysis, but it suffers two challenges. What are two challenges it suffers? First challenge is that there are too many input variables, many of the cases you can see that here, there are too many input variables, x, so many x's are there. Too many input variables do what? Too many input variables brings huge computational burden and requires big data to obtain relationship between x and y. Well, people do a lot of big data analysis, no problem nowadays, but this is the first thing it will bring. Too many input variables will bring a lot of computational burden as well as the big data issues, right. That is the first point number 1. Therefore, feature selection is the key aspects, which one is more important and which one is less important, which x is more important compared to other x. That aspects will come into picture, you need to talk about it, and that means you need to find out or you need to go back to the physics of the process, or if you are talking about a chemical reaction, chemistry of the process, you need to understand that. That is why the material science knowledge or metallurgical concept knowledge comes into picture, a domain knowledge. There you can actually throw out some of the variables which are you think not so important. Okay, that is one aspect. But second important challenge is what? This model is actually built on the but solid mathematical foundation I discussed, but they always overfit, lead to overfitting of the data. In the last lecture I showed you some overfitting of the data, right? You can go back and see the lecture. So, therefore, what is the way to handle that? This is a overfitting problem. There are two ways we can handle the overfitting problem. One is called lasso regression, other one is called ridge regression. Okay. So, lasso and ridge, let me see which one you can talk about it today, how much time you have, otherwise we will discuss the next one in the next class. So, there are two ways we can take care of this overfitting problem. One is called lasso, okay. And what do you think the full form of lasso? Ridge is easy to understand. For the full form of lasso, list absolute shrinkage and selection operator. List absolute shrinkage LS and shrinkage and what? Selection. Operator. You may get such a kind of questions in the interviews if you are looking for jobs. Ridge also similar kind of. So, here what we are doing, in these two cases both we use certain kind of a regularization term, okay, or penalty term. Some people also call it penalty, because then it cannot overfit your data. So, this is very important. Why? So, penalty term is what is used. It is like a, always we use k-fold cross validation. I hope you understand that k-fold cross validation. What is that? This is nothing but, you split the data into k-fold and k-1 fold. Let us say you have 5 sets of data. You divide into 4 set and 1 set, correct? Then you apply the machine learning model onto these 2 sets. So, one can actually do much better also, but this is the standardized things we do. So, let us talk about a little bit of lasso. What do you do? So, obviously, we are going to add a penalty term or regularization term. In case of lasso, what is the penalty term we add? We simply add a penalty term to this expression, which is smaller than a p set. So, what is that? Sum of these w's, absolute value of these w's, sum of the absolute values of the w's should be smaller than t or p set positive value. So, I write down sum of the absolute values of w's must be less than a preset value, which you can do that yourself. A t is the preset value. So, this is the extra term we add. That means this is a condition. So, once you put a condition, it is a constraint actually. So, we can call these two as a constraint regression. Here we are applying a condition. So, that is the condition you use in case of lasso, correct. In case of ridge, let me go down and write it. In case of ridge, we use some other condition. So, in case of ridge, we use basically condition of w square. You add a penalty term This is what is used as a penalty term in case of ridge. So, you understand, right? So, these two are the ones which will not allow you to overfit your data. That is what lasso and ridge is widely used. If you do not want to use, see what will happen, many cases you fit your data so nicely, your error will be only less than 1%. that means you have overfitted your data, which is not good. That will give you error, although it is not giving you high errors, very less error, but the overfitting is not good for your analysis. Remember this. In machine learning, this is very common. So, you will see that yourself when you make a model of that from a data sets. So, therefore, Lasso uses what is known as a L1, this is called L1 normalization, and this uses L21 normalization. I hope so. Let me check that. This is L21 or L12, yeah, L2, sorry, not L21, L2 normalization. So, these two are the done. So, let me just first do it for you, the Lasso thing, then if I get time, we can discuss about the other aspects, right. So, what is mathematically done? Very simple. So, simply let us focus on Lasso first. So, what is that we are doing? Same mathematical formation. So, W or rather yi is written as a W0 plus j1 to n Wj xij xj plus this term. Right. This is how we write down the yi. This lambda is called the Lagrange multiplier. Those of you who know the constraint maximization minimization, they know that the conditional minimization requires a constant called Lagrange multipliers. Okay. That is what you do. So, what is RSS, or rather why do not you write RSS? W, the optimum value of W, we can write down like this, minimize values of W, I equals to 1 to n, yi minus W naught minus sum it over j 1 to n Wj xj square plus lambda 1 to n. Okay. That is how we can measure the value. This function is minimized with a Lagrange multiplier. So, remember that this multiplier needs to be found out first. This simple mathematical analysis, how we can do optimization of any case of constant minimization problem. Okay. So, that is the how the W's are measured in case of Lasso. We can always go discuss in details about how to find out this, but you understand the value of lambda is very important, correct. If lambda becomes 0 or t is more than W naught, correct, then what will happen? This whole problem will become nonlinear or linear, actually linear regression, whole thing. The moment lambda goes to 0 or t becomes higher than this W's, okay, whatever you written, remember that. So, this is how Lasso operates. Okay. Similar thing can be written for your. So, let us I will not go into details of each these things today. So, we have to stop it over here, otherwise time is very crucial. So, as you know, so this is how actually the first normalization happened. So, no, first important aspect is how to take care of overfitting. Second one is reach, which will show you some mathematical formalism, and finally, we will get into this aspects what is called concept of probability in the next lecture. So, please do study on that. Thank you.